Good afternoon, students. We'll start with the new chapter. In the previous chapter, we have studied the energy and potential, right? And the previous class content was the energy density in the electrostatic field that we have seen, and we have winded up that chapter. Okay, we'll start with the new chapter, Unit 3, Chapter 5, Conductors, Dielectrics, and Capacitance, right? Okay, what are the topics that we are going to study here? We'll see current and current density. Okay, that we'll see. Then the continuity equation of the current we'll see. Then metallic conductors, its characteristics, properties, all those things we'll be seeing. Then the boundary conditions, what are these boundary conditions, we'll study in detail. Then boundary conditions for perfect dielectric and capacitance and examples. We'll see one by one. Okay, just I will draw one capacitor and I'll show you. Okay, these two are metallic conductors, right? Okay, in between which there is a dielectric material, right? These two are metallic conductors. This is one metallic conductor 1 and this is metallic conductor 2, in between which there is a dielectric material, right? Dielectric material or dielectric constant we call it as, right? What are these boundary conditions? I'll tell you. Yes, the boundary between conductor and dielectric. Suppose instead of one dielectric, if there are, okay, this is one dielectric slab having dielectric constant, so okay, some dielectric constant, and then another dielectric slab having some other dielectric constant, then the boundary is there between these two dielectric material. So boundary between two perfect dielectric materials, that we'll see, right? And there is a conductor here, right? Let me assume this side is conductor, then this is the free space. So what is the boundary conditions between conductor and free space? This is the boundary, right? So we will see what are the boundary conditions there in this chapter. Okay, what we are going to study today, we'll see the relationship between current and current density, that is the relationship between I and J. Then relationship between the current density and the volume charge density, J and rho v, the numericals, the continuity equation of the current, and numericals. All these things we are going to study one by one, right? Okay. Current and current density. Okay, we have defined what you know how to define current, right? The flow of charges constitute current, and here the flow of positive charges or motion of positive charges constitute current. Because okay, let me take one example of the circuit here, right? I have the source, right, and then I have a load resistor. Let me take the simple circuit, right? So minus plus, and this is a load resistor. Okay, we assume the direction of the current will be in this direction, right? You know it, right? Okay, this direction of current, we call it as conventional current. Conventional current means the flow of positive charges, means the positive charges will be flowing from positive terminal of the battery, flowing through the load, then coming to the negative terminal of the battery, right? Positive charges are flowing in this direction, but actual flow of electrons will be in this direction. The electrons, if I take the electrons, they will be flowing in this direction, right? The actual flow of electrons. So always for our discussion we consider the conventional current, right? So say we define the current as the flow of positive charges or the motion of positive charges or the rate of flow of charges, right? Dq by dt, we call it as current, and the unit of current is amps, right? Then we will define the next term, that is current density J, right? The current passing through unit surface area. Yes, if I consider any surface, okay, if I consider this surface, yes, the current passing through unit surface area. Yes, let me assume that the current is flowing in this direction through this surface, right? This is the surface area, right? So current I is flowing in this direction, right? Okay, current passing through unit surface area, we call it as current density, right? Okay, what is the unit? Amp per meter square, ampere per meter square, right? Okay, we'll see in detail the relationship between current and current density. We'll see through the diagram, and we'll try to establish the relationship between current I and the current density J. We'll see it next, right? So before that, we'll proceed with, yes, just now I told conventional current, right? So the flow of positive charges in the circuit constitutes the current, and that current we call it as conventional current. But actual flow of electrons or charge carriers and the negative charges will flow in the opposite direction to that of the conventional current, right? Then what is drift current? Yes, suppose I have a metallic conductor, right? This is a piece of wire, this is a conductor, right? So when under the influence of the field, right, under the influence of the field, the electrons are generated, right? The drift electrons we call it as. Whenever the current is flowing because of the drift electrons, then such a type of current we call it as drift current. Means under the influence of the electric field in the metallic conductor. In the metallic conductor, under the influence of the electric field, the charge carriers will move in a particular direction, right? So that we call it as drift current, right? The flow of the charge carriers under the influence of the field in a metallic conductor, we call it as drift current. Then another type of current, convection. Just you should understand this difference between these three. Convection current are also called as displacement current. Just I written here for reference. Current flowing across the capacitor. Yes, in the capacitor, right? Just let me draw it here, right? So this metallic conductor, these two are this is metallic conductor 1, this is metallic conductor 2. Is it fine? Then there is a dielectric material, right? Then the current has to flow from this metallic conductor 1 to metallic conductor 2 by passing through the dielectric material. So but this dielectric material is a highly insulating material. So how to make this as a, how this should conduct the dielectric material? So we will apply the electric field, external electric field. Under the influence of the electric field, this dielectric material means the current, the charges will flow from this metallic conductor 1 passing through this dielectric material, and it will reach the metallic conductor 2, and if it has further path, it will process, right? The current will be flowing in this direction. So under the influence of the electric field, right, the current will flow in the dielectric material. Under the influence of the external electric field, the current will flow in the dielectric material. So that type of current, or we can say the current flowing in the capacitor or flowing across the capacitor, is convection current or displacement current. I hope you are getting right. Okay, we will take the help of the diagram in order to establish the relationship between current I and the current density J. We will see, right? So this is x-axis, y-axis and z-axis, right? Then we will consider the surface, right? This is the surface area. Yes, it is placed in the xy plane. This is the surface area we have considered, right? The current I is flowing in the upward direction, z direction. So you can see the, right, the flow of charges is in the z direction. These are the lines, arrow marks indicating the direction of flow of current. So this is indicated by I. The same way, the current density, the current passing through this unit surface area, right? Current passing through this unit surface area, we call it as current density. It is also in the z direction, right? J and I. So we need some vector in order to find out the direction. So let us take the help of this unit normal vector, an vector, right? So an vector we are taking in such a way that it is normal to the surface, right? If you see, it is normal, right? It is making 90 degree with respect to this surface. So with respect to this unit normal vector, I and j, they are in the same direction as that of the unit vector. If I ask you to find out what is the angle between I and an, j and an, it is 0, right? Because they are along the same direction, right? Okay, always, okay, I hope you understood this diagram. So just we will try to, this is the first diagram, just we will try to understand the second diagram. The same surface area, fine, I as unit normal vector an, but we are considering the small surface area here, right? Okay, but observe the current and current density. They were earlier normal to the surface. Now they are making some angle theta. Current density J and current I, they are making some angle theta with respect to this unit normal vector. I hope you are getting right. So they are not in the upward direction. Slightly they are making some angle with respect to this unit normal vector theta. This is the angle theta, right? Second diagram. So we will try to establish the relationship next. Okay, we have defined the current I as the rate of flow of charges, but especially the positive charges. The rate of flow of positive charges constitutes the electric current I, right? So we express it as dq by dt. Then in the always in the field theory, we will not consider this entire surface. First we will take the smaller surface, right? Okay, the smaller surface has been taken here. We call it as ds, right? So the unit normal vector is an, which is normal to the given surface, right? I hope you understood the scenario. Next, so the small amount of current, right? The total amount of current crossing this entire surface, I don't want. Just I want to find out the number of charges flowing in this direction in this surface area, smaller surface area ds, means the current flowing in this smaller surface area. Let me call this incremental current delta I, right? So the incremental current delta I crossing the incremental surface delta s is normal to the current density. That we'll see, and we'll try to establish the relationship, right? We have defined the current density J as current passing through unit surface area. If I want the current, I is equal to the current density J into surface area, right? But what is I here? The incremental current. So it is delta I is equal to J into S. So J is the current density and delta S is the smaller surface area what we have considered. Delta S is the smaller surface area right? And the current that is flowing through the smaller surface area is delta I. I hope you got it. And the current density is, it is normal, right? Hence we take the normal component of the current density Jn. So it is written as delta I is equal to Jn, means the normal component which is normal to the surface, or it is parallel to the unit normal vector An, right? So Jn into delta S. Now I want to rewrite this equation in terms of the dot product of two vectors. So delta I is equal to j vector dot delta S vector. So what is j vector? What is delta S vector? I'll write it here. J vector is equal to the normal component of the current density, right, into the normal unit normal vector Jn. Then what about this delta S? Delta S vector is equal to the surface area, smaller surface area, and the unit normal vector. I hope if you take Jn dot delta S, right, An dot An will be 1, right? In terms of unit vector, can I write J vector dot delta S vector? I hope you got it, right? Then what is the angle between them? An, they are in the direction of unit normal vector Jn and delta S, right? So cos 0 is 1. If I take it Jn delta S into cos 0 is 1. So I am getting back this Jn into delta S, right? Okay. We are expressing in the form of dot product of two vectors. So this is a smaller surface area we have considered, but we want the total amount of current passing through this surface area. So integrate it, right? So we have this equation integrated. The total current is obtained by integrating. I is equal to surface integral. Surface integral is a double integral, right? Double integral. Surface integral of j dot ds, right? Don't worry here. Delta s and ds one and the same, right? Delta I sometimes, right? I hope you are understanding. We are mutually, sometimes delta s we write, sometimes ds we write. Don't get confused with that. So I is equal to surface integral of j dot ds. So this equation we call it as integral equation of current, integral form of continuity equation of current, integral form of continuity equation of current. Because this equation involves integration, so it is integral form of continuity equation of current. So if it is integral form, there should be differential form also, right? That is existing, means differentiation should come into picture, right? That we'll see next, right? Okay, you have to remember this equation. This is the relationship between I and J. The next second, we will try to establish the relationship between the current density J and the volume charge density rho J and rho V, right? Okay, simply I can say that the charges in motion constitutes current, right? So what is current? So what is J? Current passing through unit surface area, right? So this is the volume charge density, volume charge, right? If this volume charge is moving with certain velocity, then it is related to this current. That we will see how it is, they are related. That we will see through. So this is the final equation we are getting. That we will see how we will get this. Okay, consider the volume charge, right? The small volume charge delta V, right? Containing the small amount of charges delta Q. Okay, you can write dV also, no problem. dV and dQ, whichever is convenient way you follow that, right? No problem. So consider the small differential volume which is in the form of a cube, right? Cubical structure. It is not in irregular shape, this is in regular shape, that it is in cubical shape, right? Small differential volume, and it is containing the small amount of charges. Let us call it as differential charges as delta Q, right? Okay, how many number of charges are there in this small cube, right? So delta Q is equal to rho V into delta V, because volume charge density, how we define? Charge per unit volume, charge per unit volume, right? So if I want delta Q, so rho V into delta V, right? The same thing, delta Q is equal to rho V into delta V. Then okay, if I want the volume, entire volume, multiply by length into breadth into height, right? Length into breadth into height. Okay, so front surface, this is giving me the differential surface area delta S. It has two sides. If I multiply two sides, I am getting differential surface area. And the third side, this is giving the length delta L, differential length delta L. If I multiply delta S and delta L, it will give me delta V, differential volume delta V. Delta V is equal to the differential surface area of the front surface into the differential length delta L, right? Delta S into delta L will give me the differential volume, right? I hope you understood this. Okay, then we'll come to the second diagram. First diagram I hope you understood. Then second diagram will come. How we define current? The flow of, the rate of flow of charges, right? At a certain amount of time, right? So I will allow the volume charge to move in the x direction. I will allow the volume charge to move in the x direction. So for certain time period, say delta t, right? This volume charge has moved the distance of delta x in the x direction. But this length remains the same, but it has moved through a distance from origin to delta x. This distance is delta x, right? Okay, the rate of flow of charges means here volume charge is moving, right? Okay, we will take the help of this and we will see how we will get establish the relationship between J and rho. So the element of charge delta Q, already I told what is delta Q. Here already I told rho V into delta V, the same thing. What is delta V? Delta V is equal to delta S into delta L. So the same thing has been written here, right? So this is the elemental charge in the volume charge, whatever we have considered, right? So in time interval delta t, the element of charge, this element of charge has moved a distance of delta x. This we have seen. So we will express the current delta I is equal to rate of flow of charge delta q by delta t, right? This is the definition of current, we know. Then what is delta q? Delta q is equal to rho v into delta s into delta l. But for the first diagram, observe for the second diagram, in certain duration of time delta t, it has moved through a distance of delta x. Means I should consider which volume now. See here, I will draw the volume here. Just observe here. Just observe here. We should consider this volume. This volume. Right? The dot I will draw. Right? Cube is ahead, right? The charges, this volume charge has moved by a distance of delta x, but right, the flow of charges crossing this surface, now this is the surface it has crossed, right? So this distance is delta x, so I should consider this volume. So delta q is equal to rho v into delta s into, instead of delta l, write delta x, because it has moved by the distance delta x. Means there is a rate of decrease of positive charges, right? Earlier there was a charge here from here to here, but it has moved to distance of delta x. This has been shifted, so there is a rate of decrease of positive charges in this area, the flow of charges, right? Rate of decrease of positive charges, right? So delta q is equal to rho v into delta s don't take delta l, you take delta x. So rho v into delta s into delta x, this delta t as it is, right? What is delta x by delta t? Distance traveled by time taken. So it is nothing but velocity. So since the volume charge is moving in x direction, the velocity is also in the x direction. So delta x by delta t is nothing but vx. So the x component of the velocity, or the velocity along x direction, right? So rho v delta s vx will give me delta I. So take this delta s this side, divide it, right? Divide delta I by delta s. Delta I by delta s, what it will give me? The current density J, right? Current passing through unit surface area will give me J. So delta I by delta s is nothing but J. It is equal to rho v into vx, rho v into vx, right? I hope you understood this. Why this x is written? Because the volume charge is moving in x direction, so x component of the current density, so Jx is equal to the volume charge density rho v and the velocity component along x direction, so vx. So Jx is equal to rho v into vx. But I want to express this in terms of vector. I want to associate the direction. So instead of magnitude, take J vector is equal to rho v into the velocity vector. Means the velocity in which direction, the current density in which direction. So J vector is equal to rho v into v. If it is along x direction, Jx is equal to rho v into vx. I hope you understood this. So from this, how I will get this, I will tell you. J vector is equal to Jx into Ax, because current density along x direction. So what is the velocity vector v? The component of velocity along x direction into Ax. I hope you got it. J dot v, sorry, rho v dot, right? You are getting Jx is equal to rho v into vx, and this is in terms of vector. So this equation, this is the relationship between the current density J and the velocity, sorry, rho v, volume charge density rho v, right? Okay, just by looking at this RHS of the equation, rho v means volume charge, right? It is moving with certain velocity. If the charges in motion constitutes the current, right? The current passing through unit surface area, right? So the charges in motion constitutes the current. So this equation I have written here, the charge in motion constitutes a current. So this is the relationship between J and rho v. Then we'll try to solve few problems based on these equations, whatever we got. Given the vector current density, J vector is given, so and so A rho and A phi, Z component is absent. Then part A, find the current density at P of rho equal to 3, phi equal to 30 degrees, Z equal to 2. Just substitute the value of rho, phi, Z in this. So you will get current density at point P, J vector. Then part B, determine the total current flowing outward through the circular band rho equal to 3, phi lying between 0 to 2 pi, Z. Okay, we'll see this one by one. So part A, what they have asked, the current density J at point P. J at point P we want, right? So P is given. So 3 comma 30 degree comma 2. This is rho, phi and Z. This is 2, right? Okay, substitute the value of rho, phi, Z here in J vector. So you will get J vector at point P. Okay, I'll substitute and write. So 10 into rho square into Z. Substitute for rho, I substitute for Z. So I'll take the calculator. So 10 into rho square. What is rho? Rho is 3. So 3 square into Z. Z is how much? 2. Minus, so sorry, I will calculate this. 180 I am getting. 180 into arrow. Minus, so the second part I will calculate. 4 into rho. 4 into rho. Rho is how much? 3. Into cos square phi. So let me take cos phi. Cos phi is how much? Cos phi 30 degree. Whole square. That is nothing but cos square phi. So I am getting 9. So minus sign as it is 9 a phi. So since milli is given, milliampere meter square. So milliampere meter square. Milli is nothing but 10 power minus 3. So first part is over, right? Then coming to the part B. Determine the total current I. We should find out the total current I flowing in which direction? Outward through circular band. We'll try to draw the diagram of this, right? So that it will be very clear. So rho equal to 3, phi is 0 to 360 means it will form a cylindrical structure. It will form a cylindrical structure like this. So Z is varying from, Z is 2 here, Z is 2. It is varying from 2 to 2.8. Right? The next rho is 3. The radius rho, it is 3. Rho equal to 3. Then what about phi? If it is 360 degree, then only cylinder is formed, right? So phi is varying from 0 to 2 pi. This they have given. And this is the volume that has been formed, right? Then what they have told, determine the total current flowing outward through the circular band, right? This is the circular band. It's flowing outward through circular band means circular band is like this, means the current is flowing outward like this, not in Z direction. They have not told, right? It is flowing in the radial direction everywhere, right? We will take only one direction everywhere. The current is living like this, right? In front, back, everywhere, right? So we know the relationship between I and J. I is equal to surface integral of, compulsorily you have to write yes, or else it will become a single integral, right? So surface integral of J dot ds. Okay, J is given, no problem. But what about this ds? That we have to find out. So differential surface area. See here, the current is leaving this circular band in this direction, radial direction, everywhere. So differential surface area along rho direction I have to take, because the current is flowing outward radially through the circular band. It is not flowing in the upward direction or downward direction, right, along Z axis. So it is flowing in radial direction rho. So differential surface area along rho direction I want. So how to calculate this? We know the scale factors are 1 rho 1 and differential elements are d rho, d phi, dz. So but I want differential surface area along rho direction, leave this, multiply other quantities, rho into d phi dz. Rho d phi dz into arrow. I hope you got this. So we'll multiply j dot ds. J is there, right? J dot ds. J dot ds. Arrow dot arrow is 1 first. Right? This row will be there. 10 rho cube. 10 into rho square into rho. 10 rho cube z. 10 rho cube z. This row is already taken care. D phi dz. D phi dz. First one is over. Next. Minus. Second, arrow into a phi. This will be 0, so I will not write. This is 0, plus 0 or minus 0, whatever. Leave it. Then I is equal to surface integral is a double integral 10 rho cube z d phi into dz. So phi is varying from 0 to 2 pi. Z is varying from 2 to 2.8. So we'll try to integrate. So 10 is taken out, and even rho is also taken out because it is constant, rho cube, right? Then we'll integrate with respect to phi first, then with respect to z. 10 rho cube is taken out, right? This is taken out. So integrate with respect to phi, open bracket. So phi constant, so upper limit, the limits are from 0 to 2 pi. Then integrate with respect to z. So z square by 2 I am getting, z square by 2. The limits of z are 2 to 2.8. So what about this rho? What they have given, right? So rho is 3, right? So substitute 10 into 3 cube. So upper limit minus 5, upper limit minus lower limit. I am getting 2 pi from this, half. So upper limit minus lower limit. So I'll subtract and write. So open bracket, 2.8 square upper limit minus lower limit 2 square. 2.8 square minus 2 square. So 3.84 I am getting. So you will calculate all these things at a time. 2 into pi. So I am calculating this first. So 2 will get cancelled. 2. Okay. Just multiply all the things. I'll start from here. 10 into 3 cube. 10 into 3 cube into pi into 3.84. Yes, I am getting it as 3257.203. But what mistake I have made is, observe here, j is milli is there. This milli we have left out. J dot ds, everywhere milli should come into 10 power minus 3. We should take everywhere. So into 10 power minus 3, we will take it out. 10 power minus 3 is taken out. So here also into 10 power minus 3 into 10 power minus 3. Right, milli is given, right? So finally 3 point, take 3 units back, 3.257, right? 3.257 amps. 57203, if you want you can write 203 amps, right? 3.26, is it fine? 3.25 amps. Okay, next. Yes, a continuity equation of current, simply we call it as continuity of current or continuity equation of current. We'll see all right. So how the question can be framed: obtain the point form of continuity equation of current starting from the integral form of continuity equation of current. Integral form is this one: I is equal to closed surface integral of j dot ds. This we have seen, right? So from this we have to obtain the point form or differential form. Obtain the point form of continuity equation of current or obtain the differential form of continuity equation of current. Point form or differential form, one and them. Starting from the integral form of continuity equation. We'll see. Okay, we'll see this derivation. Yes, the principle of conservation of charges. What it is saying means the charges can neither be created nor destroyed. Yes, if I want to generate only positive charges, it is not possible. If I want to generate only negative charges, it's not possible, right? But if I want to generate simultaneously the equal number of positive and negative charges, it is possible, right? So the charges can neither be created nor destroyed. This is the principle of conservation of charges. This we will make use in this derivation, right? We will consider the closed surface, right? It is not 2D, it is 3D. Some closed surface is there, right? Some amoeba structure, something like this, right? So it is the closed surface having surface area S with current density is J in this, right? Then the total current I crossing this surface, right? So this is the closed surface. Charges are present. The current, the flow of charges constitutes current, right? The charges within, let me call it as Qi. The positive charges are there within this enclosed volume or closed surface. The flow of charges, let me assume that the charges are flowing in this direction. The flow of charges constitutes current, right? So current I is flowing in this direction. As the charges are flowing outside this closed surface, there is a decrease of positive charges within this enclosed surface, closed surface or volume. So there is a rate of decrease of charge that I will indicate by, right? The flow of charges constitutes current, but what will happen within the volume? So there is a rate of decrease of positive charges within this closed surface or volume. So that is indicated by minus dqi by dt. dq by dt means this is current, rate of flow of charges, right? Fine. Why this negative sign means there is a decrease of positive charges within the closed surface or volume, I hope so. This minus sign is for that purpose. Okay, we'll see. First, we know the I is equal to closed surface integral of j dot ds. This we know. Why we are taken closed surface? This circle indicates closed surface because we are considering the closed surface here or some volume here. So we are putting circle here. So this is S, closed surface integral of j dot ds. This is the integral form of continuity equation. Then the current I is flowing in the outward direction, right? And there is a rate of decrease of charges within the given volume. So the outward flow of positive charge must be balanced by decrease of positive charge within the closed surface, right? So the rate of decrease, already I told it, is given by minus dqi by dt. Minus dqi by dt. So I is equal to closed surface integral of j dot ds, and this is equal to the rate of decrease of positive charges within the volume or surface minus dqi by dt. I hope you got it. I can do this, right? Then I have taken the same equation in the next slide. Yes. Then what about the surface integral? We know the divergence theorem. Surface integral. So we know this. I'll write it. Closed surface integral with respect to the electric flux density I am writing. D dot ds is equal to the volume integral of the divergence of d vector over the smaller volume dv, right? So in the same way, instead of dielectric flux density, there is current density here. So I will make use of divergence theorem and I express the surface integral in terms of volume integral. So surface integral is surface integral of j dot ds is equal to volume integral of the divergence of j vector into dv. So surface integral has been expressed in the form of volume integral. So I will use this instead of surface integral. I will write this volume integral. Volume integral of del dot j into dv is equal to minus dqi by dt. Then okay, minus dq. What is this charge density? This is the closed surface containing the charges. Let me call that as volume charge, rho v, right? So what is the total amount of charges, volume charge present in this closed surface? So if I want the total amount of charge present in this entire volume, so take the volume integral of rho v into dv. The total number of volume charges present in this, right? The total amount of charges is equal to the volume integral of rho v into dv. So for q is nothing but the volume integral of rho v into dv, right? So minus d by dt as it is. This q is nothing but volume integral of rho v into dv, right? Then keeping the surface constant, what is the meaning of this? I will tell. Observe here, the current can flow in downward, right direction, left or downward. But what we are assuming, the current is flowing in this particular direction, means we are keeping this surface constant. So let me draw this surface somewhere here, right? Yes, the current is passing through this surface constantly. If I consider one more surface here, but no current is flowing, right? We are keeping the surface constant, means the current I is flowing in this direction only, in particular direction. So instead of expressing this d by dt, I can take partial derivative. When we go for partial derivative, whenever we know that it is in particular direction, so we go for partial derivative. So this d by dt is taken within the volume integral minus volume integral of this d by dt will be converted to partial derivative dou by dou t of rho v into dv. This minus sign as it is. I hope you understood, because the surface is kept constant, right? So we will take the help of partial derivative. So the rate of flow of charges, volume charges, dou by dou t of rho v means the rate of flow of volume charge, right? Okay. Then yes, the total number of charges crossing this entire volume is fine. But if I consider a point here or smaller volume here, so what are the total amount of charges crossing here? So we'll consider the smaller volume. So this volume integral will vanish. So del dot of j into dv is equal to this volume integral vanish. So minus dou rho v by dou t into del v. Means this is the total amount of charges crossing this smaller volume within this big volume, right? So it can be expressed like this. So delta v volume will get cancelled. Finally I will got delta j, del dot of j is equal to minus dou rho v by dou t. Just can you compare this equation with something? Del dot of d vector equal to rho v. Yes, what is this? Del dot of d vector equal to rho v. So this is Maxwell's first equation, also called as point form of Gauss law. Point form of Gauss law, right? So we are finding the divergence at a particular point, and what is the volume charge at that particular point? We have seen. In the same way, the divergence means we read it like this: the divergence of j vector is equal to minus dou rho v by dou t. I have explained what I actually here means. Just I will read it. Current diverging from a small volume per unit volume is equal to the rate of decrease of charge per unit volume at every point. This is the big volume, right? Right, I am considering the small volume here. Within that big volume, I am considering a small volume here, right? So del dot of J means from this small volume, the divergence of the red means the current, the charges are living in this direction. So the divergence of the current density, current flowing through this smaller volume, right? So the current diverging from a small volume is equal to what? Is equal to what? The rate of decrease of volume charge within the smaller volume. Right, if the charges are moving from this smaller volume, there is a decrease in the volume charge here, rho v. So that is indicated by minus dou rho v by dou t. I hope you understood. This equation we call it as point form of continuity equation. Point form of continuity equation, right? I am using this equation, the total amount of current leaving this surface. I am using this equation. What is the total amount of current leaving this small volume? Right, del dot of J is equal to minus dou rho v by dou t. I hope you got this. If any doubts, you can unmute yourself and speak to me so that I can clarify your doubts as and when it comes to you. Okay, derivation is over. Next, okay, you will apply this equations here. If it is a steady current means, so dou rho v by dou t means the charges are at rest. So at that time, so there is no variation. So charges are not at all moving for static charges, right? So del dot of J will be 0, right? There is no increase or decrease because the charges are not at all in motion. So del dot of J equal to 0 for steady current, right? This is just one thing we should be noting, right? Okay, we'll take up this numerical and we'll wind up this today's class. 3:10 time. Okay, fine, we can finish this. The current density is given in cylindrical coordinates. Already is telling it is given in cylindrical coordinate system. J vector is equal to minus 10 power 6 z to the power of 1.5 into Az. Means cylindrical rho component is not there and phi component is only z component is there. Ampere meter square. In the region rho lying between 0 to 20 micron meter, yes, radius is given. Then for rho greater than or equal to 20 micron meter, J is 0. See here, just cylindrical coordinates means, okay, just I made it slant here. Okay, this is radius rho. If rho is varying from 0 to 20 micron meter, so this is 20 micron meter. So for rho greater than 20 micron meter, J is 0 outside. Means J exists, current density exists within this given volume or closed surface, outside which it is 0. That is the meaning, right? J is 0. Find the total current passing crossing the surface Z equal to 0.1 in the AZ direction. So if I take Z direction in this way, right? So if I consider Z equal to 0.1 here, so where Z equal to 0.1 meter, right? So the current is flowing in this direction, Z direction, current I, right? This is the current I is flowing in this direction, crossing this surface, which is placed at Z equal to 0.1. So what they was, find the total current I we have to find out. So part I will see in AZ direction. This is the Z direction, right? If I take, so I will see X, Y and Z. Z direction, right? Okay. So I is equal to what? You know the relationship between I and J, right? I is equal to closed surface integral of J dot ds, right? Oh, J is given, no problem. Only Z component is there. What about ds? So differential surface area, it is placed here at Z equal to 1 means it is, means in the Z direction we have to take. So ds Z I have to take. Differential surface area along Z direction, right? So how to find it? So cylindrical coordinates means 1 rho 1 are the scale factors and the differential elements are d rho, d phi, dz. But we want differential surface area along Z direction, leave this and multiply other things. Rho, d rho, d phi. Rho, d rho, d phi into az. So we'll expand this, we'll substitute here. I is equal to surface integral is double integral J dot ds. So we'll take the dot product of J dot ds. J is here, ds is here. So az dot az will be 1. Remaining things will multiply. So minus 10 power 6 z to the power of 1.5 into this thing. Multiply z components, rho into d rho d phi. So rho is varying from what? 0 to 20 micron meter. 0 to 20 micron means 10 power minus 6. Then phi is varying from, yes, if it has to form a cylinder or closed surface means phi has to vary from 0 to 360 degree, that is 0 to 2 pi, right? We'll say this. So z is constant. What is z? Z is 0.1 meter. This is surface they have given. Z is 0.1 meter, right? So we'll substitute and take it out. Minus 10 power 6. Then what is the value of Z? Z is 0.1. So 0.1 whole to the power of 1.5. Z to the power of 1.5. Next, open bracket. Yes, we'll integrate with respect to rho first. That is rho square by 2. Rho is varying from 0 to 20 into 10 power minus 6. Then next, integrate with respect to phi. Phi is constant. So phi is varying from 0 to 2 pi. Okay, we'll see this. Okay, just I will multiply. Minus 10 to the power of 6 into 0.1, open bracket, 0.1 to the power of 1.5. 0.1 to the power of 1.5. What I am getting, I'll write. So minus 31622.776 I am getting. Yes, this I am getting if I multiply this. Then next half, we'll see what will upper limit minus lower limit I will do. So upper limit rho square, right? So 20 exponential minus 6, open bracket, 20 exponential minus 6 whole square, because rho square is there, right? So I am getting 4 into 10 power minus 10. Then minus lower limit, leave it, it is 0, into upper limit minus lower limit, I am getting 2 pi. So 2 will get cancelled, 2 1 ja, 2 2 ja 4. So multiply all the things. So minus 31,622.776 into 2 into 2 pi into 2 pi into 2 into pi. So and exponential into 10 power minus 10 also I will take, into 10 to the power of minus 10. So I am getting it as I is equal to, so I will express in terms of micro, minus 39.73 into 10 power minus 6 amps. You can observe here minus 39.7, micro means 10 power minus 6, right? So minus 39.73 into 10 power minus 6 amps, right? This is the total current that is flowing through this surface placed at Z equal to 0.1. Then we'll take up part B. So if the charge velocity V is given 2 into 10 power 6, velocity is given 2 into 10 power 6 meters per second. This is given at Z equal to 0.1 meter. At Z equal to 0.1 meter. Yes. And what they have asked? Find rho V. Volume charge density they have asked. So we know the relationship between, if the volume charge moves with certain velocity, it's nothing but current density. We know the relationship between J and rho V. J is equal to rho V into V. It is in terms of vector, but V is given in magnitude is given. So I will not concentrate, just take the magnitude on both the sides. So J is equal to rho V into V. Just I am taking the magnitudes. J is equal to rho V into V. I can write this. So what is asked? Rho V is asked. So rho V is equal to J divided by V. Okay, what is J? So J vector is given. So I will write J vector, what is given? So minus 10 power 6 Z to the power of 1.5 into AZ. So if I want J, the magnitude, so it is minus 10 power 6 into Z to the power of 1.5. JZ into AZ, right? So this will give me magnitude. So let me write, I'll substitute here 10 power 6 into Z. What is Z here? Z is 0.1. So 0.1 to the power of 1.5 divided by, what is velocity? 2 into 10 power 6. So we will calculate here, we will get rho V. So let me calculate, minus, open bracket, minus 10 to the power of 6 into open bracket 0.1 to the power of 1.5 close bracket. So I'll calculate this first, divided by 2 exponential 6. So I'm getting it as minus 0.0158 what is the unit? Coulomb per meter cube. Charge per unit volume, right? Coulomb per. Let me check. Yes, they are expressed in milli. Milli means 10 power minus 3. So I will express in milli only, no problem. Milli means 3 digits. Take 15.81 milli coulomb per meter cube. Right? Next part C. Part C will take up. If the volume charge density at Z is how much? Here Z is different, 0.15 they are given. Then rho V is given minus 2000 coulomb per meter cube. Minus 2000 coulomb per meter cube. Then find the charge velocity. It is asked to find out V. We will use the same relationship, this one. Right? So J is equal to rho V into V. So we want V. V is equal to J by rho V. So what is J? The same thing. This one minus 10 power 6 into Z to the power of 1.5. So J is minus 10 power 6. What is Z here? Z is different here. 0.15. So 0.15 whole to the power of 1.5. Rho V is minus 2000. So minus it will be plus. So I will calculate how much velocity we are getting. Okay, I will calculate numerator 10 to the power of 6 into open bracket 0.15 to the power of 1.5. So I am getting this, then divided by 2000. So I am getting 29.04 meters per second. Right? So 29.0 meters per second. Right? Okay, fine. I will stop this today's lecture today here.